Okay. Questions? Yeah.
Can I ask a question about that?
Sure.
The last question, it says to show the mechanism and form rearrangement for both SN1 and SN2.
Wait.
How would I can do it with SN1, but I'm not quite sure.
Wait, show the mechanism for forming the rearranged SN1. Okay, and SN2 products. Okay. We'll keep it the same. So which one's throwing you?
The SN2.
Okay. So the SN2 is, so let's imagine that I'm going to take this and I still can't do, I can't do SN1 or SN2 on this molecule without protonating the OH. So the first step is going to be to do what?
So the electron arrow from the comparing the O to the H.
Right. So I'm going to protonate the OH. So if I protonate the OH, I have an oxonium ion. And if you're going to do a 1 mechanism on this reaction, you have to lose the water to form the carbocation. So you have to basically lose the H2O and form that carbocation. So as far as the SN1 mechanism goes, once you form the carbocation, and then once you protonate the OH, and then you form the carbocation, now is when you're going to rearrange. Okay? If you don't rearrange at this point, you're doing an SN1 mechanism with no rearrangement. So at this point is the place where you would have to do the rearrangement.
You can do the SN1 where you add the bromine to that.
Yeah, but if I add the bromine to this, if I add the Br minus to this one right now, then what I just did was I just did the SN1 mechanism without rearrangement. And that's not what I'm asking for. I'm asking for the SN1 mechanism with rearrangement. So you have to rearrange that you have to rearrange this carbocation before you do the bromine addition. So that's what the mechanism will be with rearrangement. So what you sent me was fine for the not rearranged, but you've got to go through the steps in order to get to the carbocation and then rearrange it and then continue with the reaction.
So how do you rearrange it and keep it like SN1 versus an SN2?
Well, so the SN1 rearrangement would just be simply to shift this hydrogen over to do the 1-2, to do a 1-2 hydrogen shift or hydride shift, and then you're going to end up with the carbocation on the tertiary carbon. And then you add the bromine. So that would be the SN1. So this is now If your Br minus comes in and adds to that carbocation, this is now the SN1 with rearrangement.
And then for SN2,
For SN2,
we've got the oxone, which is bringing from an H over.
so with the with this oxonium ion, if we wanted to do SN2, let's say the Br minus wants to come in and add and attack that carbon. Can it do that? Well, maybe, but let's say for the sake of argument that maybe that isopropyl group, maybe this isopropyl group over here might block that bromine from doing that. So if I wanted to do SN2 then, well, I can't really do SN2, right, without, I can't do SN2 without, okay. Let me read you the way I want the question to go. Show the mechanism for forming the rearranged SN1. So the rearranged goes with SN1. It does not go with SN2. It just goes, this just goes SN2. So now you're going to have the bromine come in and attack the carbon, and then you're going to do your SN2. The one that's got the leaving group attached. So it's rearranged SN1 and the normal SN2 product is the way that question the question should read. I can see where the confusion was there. Because at this point, you can't have a rearranged SN2, because by definition, when things rearrange, they go to a carbocation intermediate, which changes their mechanism to SN1. So SN2s are on their own. So that's unrearranged. It's rearranged SN1. Now, for the other problems, the rearranged goes with SN1 and E1. So you're going to do the carbocation rearrangement, then you're going to do the SN1, then you're going to write the E1 products as well. Okay. What else?
Oh, about this.
Anything?
I was kind of confused with one, like, for the concourse. I thought to do part of the cation, but didn't come up with stuff there.
Okay. So you're reacting this with methanol, CH3OH, and it's asking you to do the rearranged SN1 and rearranged major E1 product. You're supposed to show the mechanism of that. So what should I do first? Right, so what should I do? First step.
Oh, you remove the CO.
I'm going to break the carbon-chlorine bond and form the carbocation. Okay. Then what are you going to do? Okay, we're going to do a rearrangement. So what's rearranging? All right, somebody help her out. Yep. So yes, the carbocation will move, but what else will move? The hydrogen. So you have to show the hydrogen then doing a 1-2 shift so that the hydrogen then moves down here now to this carbon, and then the plus charge moves up. So it's a combination of both the plus charge moving and the hydrogen moving. Where else could it have moved? So remember, I think we did this. When did we do this? When did we do this whole hydrogen shifting, and particularly in this cyclohexane ring? I think it was yesterday. Pretty sure it was yesterday. We started it, yeah, we started it on Monday. So here's my alpha carbon, here's my beta carbon, here's my beta carbon. So the alpha carbon is going to form the carbocation. So when you form the carbocation, you can only shift the plus charge to a neighboring beta hydrogen, or beta carbon. In order to do that, you need a beta hydrogen to move, to shift over in order for the plus charge to shift. So I think we could move this hydrogen, or we could move that hydrogen. We could use this, we could move this beta hydrogen, or we could move that beta hydrogen. So why did we shift the top beta hydrogen that I'll call beta hydrogen A? Why did we shift HA instead of HB? Because I get a tertiary carbocation instead of a secondary one. So that's why we're shifting that's why we're shifting the top hydrogen. So once you do that, then you're going to add the methanol to it to form the SN1 product, or you're going to lose a beta hydrogen plus to form the major E1 product. And yesterday we didn't do this problem with a methyl group, we did it with an ethyl group. but it's pretty much the same thing. So that's what we need to do. We need to form the carbocation. For problems 1 and 2, you need to form the carbocation, rearrange it, and then do the SN1 and the E1. And you're showing the mechanism to form the most substituted alkene for the E1, because this is the major E1 product. Does that make sense? You just got to do it. What else?
So at the end of last class, we were starting to talk about alcohol. Like what, how do we know like what type of acid
Okay.
to use, and
Sure.
how we know if it goes
Okay, so if I have an alcohol and I want to do an SN1 or an SN2 substitution, I know I have to add H plus to it, because the H plus is going to protonate the OH, and the only way to make the OH leave is to protonate it with an H plus. Okay. Now it can leave. So if I want to do substitution, what do I want to replace that OH with? No. Well, so I want to make it leave, but then I want to substitute something there. So will the water leave? Yes. The water will leave. I'll lose H2O, and I'll form the carbocation. So once I form the carbocation, then if I want to do substitution, what do I want to add to that carbocation? So the idea here is if you want to do SN1 or SN2, you need to use H plus in order to make the water leave. But then what are you going to substitute for that OH group?
I thought you said SN2 can be carbohydrate.
Right. So I'll show you what an SN2 looks like in a minute.
So this is just SN1.
So right now it's SN1, but it doesn't have to be. So if I want to substitute this OH, I need to use an H plus and then a nucleophile with that that's going to go ahead and come in and substitute. So this is where we said we could use HCl, we could use HBr, we could use HF, we could use HI. So if we want to substitute the OH group with a halogen, then I just use HX. So generically this would be HX, H plus, X minus, where X is the halogen. And so then my halogen would come in, add to the carbocation, and I would do my substitution. So if I want to do substitution right now, all I can substitute the OH with is a halogen. And that'll be either SN1 or SN2, depending on the type of alcohol I'm using. Now, what do I mean by type of alcohol? Well, this is what kind of alcohol. The carbon attached to the OH is primary, secondary, or tertiary. It's secondary. So that one is a secondary alcohol. So it could go by either mechanism, actually. I could say that I'm losing the water to form a carbocation, but I could also make the case that once I form the oxonium ion, since it's secondary, that my, let's say, Br minus comes in and kicks off the water that way. So that, because this is a secondary system, we could say a secondary system could undergo SN1 or it could undergo SN2. And so if the Br minus comes in and kicks off the water, I'm going to go through, if I do that, then I'm going to say, well, that's an SN2 mechanism, which means that it's going to undergo the same trigonal bipyramidal transition state as before. It's just that the ring is now attached to that carbon that's being attacked. So this is the ring. That's the six-membered ring. And so the Br minus is going to be delta minus, and the oxygen is going to be delta
So,
That's not the answer to my question. But go ahead and ask.
but from the discussion Monday, if what you give is the question, the molecule you know that this A would be one answer, you might see S1 and S2.
I might just say make a choice. But in this case, because this is a secondary system, you could write valid SN1 or SN2 mechanisms for this. Right. So if it's either or, you could write either one. But I may tell you which one to write. So in this case, the question is, we did a lot of SN1 reactions because we protonated the OH and the water left. I know we did one SN2 reaction yesterday because I remember going through this transition state. Because I remember asking, what's the partial charge on the oxygen? Anticipating that people would say it's delta. No, it is delta positive, but I was anticipating people to say it's delta minus because in all the other examples we've done, it's been delta minus on both sides. But it's not in this case because that oxygen is going from +1 to 0, so it's delta plus. So we could do an SN2 reaction with this. What we would have to do is we just have to protonate the OH, have the nucleophile come in and attack, go through the transition state, the trigonal bipyramidal transition state to get me to the product. So the point with this was, this is SN. So I'm substituting the OH with a halogen, and that's all I can do right now. So we focused yesterday on, all right, OH isn't leaving by itself, right? Right? I feel like I'm talking to myself. So the OH isn't going anywhere on its own. So what did I have to do to it? Protonate it. And then once I formed the carbocation, or I didn't form a carbocation and there's a nucleophile that comes in, I'm going to automatically do SN, but my question was, what if I don't want to do SN? What if I want to do E? What if I want to form a double bond? And then I asked you, okay, what should we do? And there was a lot of silence. And then the ultimate answer was, if you want this to go E, what should you do? What? I don't want to do any SNs. I want to do E. Right, I'm using sulfuric acid. Why? The answer to the question of, I don't want to do SN, I want to do E, well then don't have a nucleophile. Use an H plus that doesn't have a nucleophile associated with it. So that's when we got into saying, well, what if I did this reaction, the same reaction with H2SO4? If I did this reaction with H2SO4, now I still have a source of H plus, but now my SO4 minus, my conjugate base of this strong acid is a non-nucleophile. And then I think I remember saying, well, why is it a non-nucleophile? So the resonance structures give it stability, and whenever we have in an acid-base equilibrium where I'm forming a very stable conjugate base, what happens to that molecule's basicity? If this is very stable, that means that this is a weak to non-base. And so if it's a weak base, or it's not even a base, then it's not going to be a very strong nucleophile. And in this case, not only do we have this being very stable and very weak, you could also make the argument that there's sterics involved here that are going to keep that from adding to the carbocation. So if I now want to do elimination, I should use an acid that doesn't have a conjugate base that acts as a nucleophile. So this is not a nucleophile. It will not act as a nucleophile. And so if it won't act as a nucleophile, and I apply a little heat, that's what the triangle stands for, is heat. If I apply a little bit of heat to this, what I'm going to end up doing is forming the double bond and water, and have this totally going E. And in this case, this mechanism would be an E1 mechanism because I'm going to form a carbocation. So that's where we changed our focus. We said with alcohols I have a little bit more control over when to do substitution and when to do elimination. And so when do we do elimination? Whenever we use sulfuric acid and heat, because the mechanism for this would look like my H2SO4 is my source of H+, so my OH is going to be protonated by the H, so I'm going to form my oxonium ion. Since this is a secondary carbon attached to the water molecule, or what's going to become a water molecule, or sometimes people call it an incipient water molecule, which I think just means it's going to become a water molecule. Then I'm just going to break the carbon-oxygen bond. I'm going to lose my H2O and form my carbocation. But now when I form my carbocation, there's no nucleophile to come in and add. And so what's going to happen? It's going to undergo E1. So now I'm back to, okay, my carbocation is my alpha carbon. There's 2 beta carbons here. Do they have hydrogens? Yes, there's 2 beta hydrogens. Which one am I going to lose? The top beta hydrogen or the bottom beta hydrogen? Either one, because I'm going to form the same product. So now my H plus, I lose my H plus, either one of those beta hydrogen, and so now I'm going to form my double bond. So if we take an alcohol and we react it with sulfuric acid and heat, or you can also use H3PO4, which would be an alternative reagent. If I use the H2PO4 or H3PO4 or H2SO4 and heat, I'm going to basically lose water and I'm going to form the double bond. So I have a choice with an alcohol. Do you want to substitute? HX. Do you want to eliminate? H2SO4. So that's where we made that change right at the end of class. And the last thing I said was, this is called a dehydration because I'm losing water. So this is a dehydration reaction. And then one question that I didn't ask that I will now ask is, so in this mechanism, which is protonate the OH, form the oxonium ion, lose the water to form the carbocation, lose the H plus, what is the role of the H plus in that mechanism? What about the H plus? It's used at the beginning. It's generated back in the last step. So it's not a reactant because it's used and regenerated. So there's no net loss of H plus. What do we call those kinds of species? It's a catalyst. And it speeds up the reaction. But it's a catalyst because catalysts are used in one step but regenerated in another. So the official role of the H plus is as a catalyst. So that's its role. And that almost ends everything on E1. Almost. Does that make sense? So this technically is what kind of mechanism? Taking cyclohexanol, reacting with H2SO4 to form the final cyclohexene product. How would we classify it? Number one, am I doing substitution or elimination? Elimination, because elimination always gives you a double bond. So it's E. E1 or E2? Why? Because it's a carbocation. So it's E1 because it's a carbocation. So what would your next question be? That would be my next question. What would an E2 look like in a dehydration reaction? Which I would then turn around on you and say, okay, we can't do this with a carbocation intermediate. So what kind of alcohol should I use at the beginning? Secondaries and tertiaries, can they form carbocations? Primary. So this is a reaction that you would get, or a mechanism that you would get if you took, let's say, butanol and you reacted H2SO4 and heat with this. So this is a primary system, and without rearrangement, this system is going to have to go through elimination with no primary carbocation. So what's H2SO4? It is a source of H+. Right? Tell me what the first step of the mechanism should be. I would call that protonating the OH. Because whenever you react an oxygen species with H+, what's always the first step? Protonate the OH. Okay, great. All right, so I have my protonated OH, which is now my oxonium ion. What happens next? What should I do next?
LED.
I'll give you a choice. You can tell me what you should do or what you shouldn't do.
Would you take the OH?
You mean the whole water molecule off?
Yeah.
I don't know. You have a question mark at the end of that. Is that a should or shouldn't? Should we lose the water or shouldn't we lose the water? Should not. Hannah?
Could you use the water in the green?
Okay, that's a new suggestion. If we're going to lose the water, then we should do what with, so here's my alpha carbon again. And in this case, I have uno beta carbon, that's it. So if I'm going to lose that water, what should happen to the beta hydrogen? Should lose it too, right? Or did you want to shift it? I could do two things with that beta hydrogen. I could shift it over and then kick off the water all at the same time. Or I could just lose it and the water molecule and form the double bond directly. Is that what you want to do? Is choice B? So in other words, I shouldn't lose the water. Why not? Because if I just lose the water molecule, what am I going to form? What kind of carbocation? A primary carbocation. Am I allowed to draw those? Didn't I draw one yesterday? I think I drew one yesterday, right? Because you guys told me to. So no, we can't just lose water. So how about we lose the water, but at the same time, let's lose the H plus and have that pair of electrons go to form the double bond. And if you wanted to, you could say, well, let's, we could shift the H plus, but if I specifically said no rearrangements on this, then we would lose, so we're going to lose an H plus here. I'm going to lose the H plus, and I'm going to lose the H2O. And what am I going to do? I'm going to form a double bond between which two carbons? The alpha carbon and the beta carbon. So when I'm doing these dehydration reactions, I'm doing E1 or E2. And we haven't talked about E2 with alkyl halides yet. But in E1, what did we always form the double bond? We always formed the double bond between the alpha and the beta carbon. In this case, there is only one beta carbon, so that's where the double bond has to go. So that's probably the next question you would want to ask, would be what would the transition state look like so if I'm going to draw that transition state, I need dotted lines between all the bonds that are being broken and made. So I need a dotted line between what and what? Between the C and the H. And the CH2 and the O. And then where else do I need the dotted line? Between the alpha and the beta carbon, because in that case I'm forming my double bond. So I'm breaking my CH bond to form the H plus, I'm breaking my CO bond to form the water molecule, and I'm forming the double bond. So that would be my transition state, except what am I missing? Charges. So who gets what charge? So a delta positive on the H because it's on its way to make an H plus. And a delta positive on the O because it's on its way from +1 to 0. So what kind of mechanism is this? I'm forming a double bond, so it's E, no carbocation intermediate. So this would be classified as an E2 mechanism.
What if you were able to do put action?
So if I did the other rearrangement, then what would happen is that the plus charge would end up on the beta carbon. And then I'd have to relabel that beta carbon now as an alpha carbon in order to lose either a hydrogen on carbon 1 or carbon 3. So there's two possible. So if I did the shift, so if I did the hydrogen shift on this, I would end up with this carbocation. Then the mechanism would change because now it's going through a carbocation, so now it's E1. This now would become my alpha carbon. This would be a beta carbon, this would be a beta carbon. Let's call this beta carbon A, and let's call this beta carbon B. My mechanism now shifted from being E2 to E1. So where should the double bond go? Should the double bond go between the alpha carbon and beta carbon A or beta carbon B? And let's vote. So what would be the final product? Would it be this one, which would be product A? Or would it be that one losing the H plus off carbon B? Would it be carbon B? Or would it be C, 50-50? So is it A, B, or both C? What do you want as D? Well, if they're not 50-50, then I want the majority. When I say major product, I mean majority product. So if it's not 50-50, it's either A or B.
So you want the majority.
Right. And if they're 50-50, then I want C. Yeah, I want the major product, which is always the majority product. Okay, what did we get? We got 9 to 1 to 1. 9 A's, 1 B, and 1 C. Why A? One of the 9 that voted A. It's more substituted, which means it's more stable. Is that the major product of this reaction, the more stable product? Yes, because this mechanism is now E1. Because I've now got a carbocation. And the question would be, what's the major product of the E2 reaction? But here's the thing. For these dehydration reactions, for it to go E2, that means the OH has to be attached to what kind of carbon? Primary, secondary, or tertiary? Primary. Right? It's got to be a primary carbon. Why? Because to be 2, it means you can't have a carbocation intermediate. So if you have a primary carbon, how many other carbons do you have attached to it? 1. That's the definition of a primary carbon. If you only have one carbon attached to you, how many beta carbons do you have? 1. That's it. So how many products can you form? 1. So if you have a primary alcohol, you're only going to have 1 carbon attached to it, and if you do not do rearrangement, you're only going to get that double bond between that carbon and the one it's attached to. So there is no question about which is the major product. You only get 1 product.
So E2 only works with the primary. Can you use a secondary if you don't rearrange?
No. Because if you protonate an OH group attached to a secondary, the water's going to want to leave. And the question is, can it? Yes, because you're attached to a secondary carbon. So there is only one kind of E2 reaction for an alcohol, and that is an alcohol attached to a primary carbon. And it would have a mechanism that looks like this. And if I said write the mechanism without rearrangement, you would lose the H plus instead of shifting it. Alex?
So we were able to do the iron because we made it into the carbon.
Right, because we shifted it. So when the hydrogen shifted over, that left us with a secondary carbocation. Did that follow our rules? Yeah, we did 1 shift. Did we form a more stable carbocation? Well, primary versus secondary, yes. So we could have that happen. And this is one of these situations where I would have to tell you to shift it. And so the beta hydrogen would have shifted over. And then once you do a shift, the key is, with all of these that we've done for the last 2 days, the key is once you do a shift, you have to relabel the alpha and the beta carbons. Because initially the alpha and the beta are based on the leaving group. The leaving group leaves, you form a carbocation. The minute you rearrange it, you now have to relabel alpha and beta to get the right elimination products. So in this case, I had a different set. And the only reason I asked you this question was I wanted to make sure we remembered what the major product is in E1. Right? And that is always the most substituted, most stable alkene. So that's the only type of E2 that can occur with an alcohol, which is the perfect segue into, can you do E2 with alkyl halides? Well, if the answer was no, then I'd say no and we'd move on, but I'm not going to do that. The answer is yes. So we need to talk about how you would do an E2 mechanism with an alkyl halide. And so let's start with our one chlorobutane molecule that we just ended with. Now, if I'm going to do E2, I'm going to have to get aggressive with this molecule. And the question is, well, how am I going to become aggressive with this alkyl halide to do an elimination that doesn't involve a carbocation? And what I need is, well, take a step back. when I've lost the H plus in all of the 1 mechanisms, right, when the H plus has come off, in the book we talked about the idea that maybe there's a solvent molecule where you show the arrow sort of catching the H plus as it comes off. But the solvent molecule, if you show an arrow going to the beta hydrogen, it's not ripping it off. It's just like the H plus falls off and it's got to go somewhere, so it bonds to the solvent. That's kind of the way the beta hydrogens fall off now. But now I want to be really aggressive and I want to rip the hydrogen off. And in this case, the hydrogen I want to rip off is that beta hydrogen, because there's only one. So what kind of molecule can I use to absolutely just take that beta hydrogen away? I'm going to need something that's a strong... I want to remove this H as an H plus. So what would react with an H plus? Yeah, but now I want it. I don't want it to act as a nucleophile, because nucleophiles we're thinking of attacking to add bonds. In this case, I want to just rip the hydrogen off. So I want something that's a strong nucleophile, but it's also a strong base. So the thing I want to remove here, I want to remove that hydrogen with a strong base, which I'm going to label right now B minus. So B minus is my strong base. And so if I use a strong base with this, the B minus is going to come in, rip the hydrogen off as an H plus. The CH bond then is going to break because that pair of electrons is now going to go to form the double bond. And if I form a double bond between the CH and the CH2, what's going to have to happen to the CH2? It's going to have to lose the chlorine, or else I'm going to get stuck with 5 bonds. So now I'm going to take a base, remove the beta hydrogen, have the pair of electrons move to form the double bond, and have the leaving group leave, all in one concerted step. So what's that transition state going to look like? You tell me. What bonds am I making and breaking? ClCH2, that's a partial bond. No, you have your hand up.
I was going to ask, the bond between the CH2 and Cl, that like tends to be C.
Right. So that pair of electrons is going to go to the Cl. So after our discussion yesterday, it should probably look like that. It should be pointed more towards the Cl than out in the middle of nowhere. But at least that's the right direction if it's going out in the middle of nowhere. Okay. So where else do we have partial bonds? What else am I making? Alex? Partial double bond. Partial bond between H and C, and partial bond between H and B. So the base is getting an H plus, the carbon is losing the H plus but forming the double bond, and the CH2 has to lose the Cl or the leaving group or the halogen leaving group in order to keep from having 5 bonds. So that's our transition state. Minus charges, who gets a charge? Cl gets a delta minus, and then the B gets a delta minus as well. You can put the delta plus on the H, but technically it's really not a delta plus because it's going to the base. So in the end, I'm going to get a BH plus 1 plus 1 butene is my BH plus my butene plus my Cl minus. So this is elimination. If we went back to all of the kinetics we talked about, since this is a concerted one-step mechanism, the rate would be dependent on the concentration of the base and the alkyl halide. So the rate equation for this would be rate equals K times concentration of the base times the concentration of the alkyl halide, which means that this is a blank molecular reaction. It's a bimolecular reaction, which means this should be E2, although now with our redefinition of E2, it still is E2 because it doesn't involve a carbocation. So now we've got the ability to form an alkene directly from the alkyl halide using a strong base. And so that's what our mechanism would look like, Hannah.
Are the E1 and E2 rate equations the same?
Yes, so the E1 rate equation would be rate equals times concentration of alkyl halide. And there's no nucleophile in that, really. Right, there's no nucleophile in forming the double bond. It would make it go faster, but it really wouldn't affect the rate equation. Because the rate equation depends on throwing a changing concentration. Oh, and if we're going to do this with the alcohol, since the acid we're using is a catalyst, the catalyst will affect the rate, right? So, not in this case. The H plus would be part of the rate equation for an alcohol, because that's what the catalyst does. Catalyst affect rate, doesn't affect equilibrium position. So now I can do an elimination. Actually, I can do a controlled elimination on an alkyl halide. So what did we say about E1? Well, we didn't say anything. What did I say about E1? I said E1's kind of like a nuisance reaction, right? It's a side reaction that occurs with SN1. Unless I have an alcohol where I can force the reaction to go elimination by using sulfuric acid. This allows me to do an elimination on an alkyl halide and not do any substitution. So now all I got to do is figure out what my strong base should be. That's all I have to figure out. Oh, and then if I have, instead of 1 chlorobutene, if I have 2-chlorobutene, where now there's an alpha and there's now 2 beta carbons with beta hydrogens. I can still get my 2 products, my 1-butene and my 2-butene. And so it would be really nice if I could use one base and get one product and use another base and get the other product. So that I can control what my major product should be in situations where I can form more than one. That would be really nice. That would be a wish list. And to be honest with you, if organic chemistry is going to be successful, which it is, right? That's why you're taking it. If it was unimportant, you wouldn't have to take it. But if you're going to do synthesis, if you're going to make plastics, drug molecules, I need that control. I need to say, well, I want to make this product this time, but I want to make the other product the other time. And that's what I was getting at with the alcohols. I want to do substitution. I have reagents that I can do that with. I want to do just elimination. Well, I have reagents that I can do that with. Except in that case, when I did eliminations, I was limited to E1, so I was limited to only form the most stable double bond. It would be nice if now I could form the least stable double bond. Okay, so that's what we have to think about in terms of, well, this would be nice. This is my wish list for E2, if I had one. So the first thing we've got to deal with is this. That strong base is also a strong you said it before, Jenny. It's a strong nucleophile. So if I have a strong base that's a strong nucleophile, what's stopping my strong base / nucleophile from attacking the primary carbon and kicking out the chlorine? Nothing. So I've got to design a base that's a strong base, but it's not nucleophilic. That it won't attack as a nucleophile. So the base that I'm going to use for that is going to be NH2 minus, what's called amide. And for reasons that are beyond the scope of this class, right? Whenever I can't answer a question, well, that's beyond the scope of this class. This NH2 minus is a strong base, but it is not nucleophilic. So this is a small strong base that is a non-nucleophile. It's not nucleophilic. So if I react NH2 minus with my 1-chlorobutane, it's going to do E2. It's not going to do SN2. So that's one tack I can use, is to find a base that is strong but not nucleophilic. Now that's a unique one. NH2 minus is unique. One of the things that makes SN1, SN2, E1, and E2 really difficult are molecules that have alkyl groups attached to an O minus. So the RO minus is called an alkoxide. Why? Because it's a deprotonated I'll be back in a minute. It's a deprotonated alcohol. So the oxide is basically is a suffix we use to indicate that something has a negative charge on it. So an alcohol, when it's deprotonated, becomes an alkoxide. Problem with alkoxides is our favorite alkoxides are things like CH3O-, which comes from methanol, which is called methoxide, or CH3CH2O-, which is called ethoxide. And sadly, your book uses these. They kind of use it as a substitute for NH2-. The problem with methoxide and ethoxide is that they're strong bases. There's no doubt about that. But they're also strong nucleophiles. And in Organic 2, we're going to talk about using them as nucleophiles. So I'd rather not talk about using them as bases right now and then come back and say, oh yeah, no, they do. Their major tendency is to be a nucleophile, which is what their major tendency is. So you'll see in the book they use these to do E2 reactions. The critical part is these are small bases. I'm going to use NH2- because NH2- is my favorite small base, and it just doesn't want to act as a nucleophile. Now there is an alkoxide that I can use that will be a strong base, but it will not be nucleophilic. And in order to design that alkoxide, what I have to say is, so if you want a nucleophile to not act as a nucleophile, the approach is the opposite approach of how we did SN1 and SN2. So why didn't a tertiary halide react in an SN2 reaction? Too much steric hindrance around the carbon that had the leaving group attached to it. Well, what if I take and say, you know, I don't want my nucleophile, I don't want my alkoxide to act as a nucleophile, so how about I make it sterically hindered? So now I've got a sterically hindered nucleophile so that it won't want to do SN2. And that would be a brilliant approach. And so the easiest one I could think of is to use what's called tert-butoxide. And tert-butoxide usually has a K+ on it. So this is potassium tert-butoxide. I'll usually use it without the potassium, but we might as well have this discussion. I can't go to, if I told you, hey, go to the stockroom and get me some methoxide, you'd come back and say, well, either they don't have methoxide, or well, what should I get? Should I get sodium methoxide? Should I get potassium methoxide? Should I get lithium methoxide? Because you can't just go to the stockroom and get methoxide ion. There has to be a counter ion to it. So what's the counter ion? Sodium, potassium, lithium. The thing is, it doesn't matter in this class. It doesn't matter what that counter ion is. It's just a spectator ion for general chemistry. Does it do anything? In reality, it does, but we're not going to have it do anything. So I will use a tert-butoxide without the potassium, because if I put the potassium in there and you don't remember that it's a counter ion, then it just shows up all sorts of places. My favorite is like when the potassium shows up like on an inside of a benzene or a cyclohexane ring. That's my favorite because it's like, well, what is it doing there? But that's where people put it. So in order to save you points, we don't usually use the counter ions because then they show up in all these places. But realize it's got to have a counter ion. So I personally like potassium tert-butoxide or tert-butoxide because now it's a strong base, but now it's sterically hindered. So it's not small. Is that going to change the way it reacts? Yeah. But then I got a small base that does one thing, I got a sterically hindered base that does another. That's going to help me out because I use one, it does one thing, I want the other, I do the other thing. I use the other base. There are more of these. The book may talk about, there's an N- with 2 isopropyl groups attached to it, usually with a lithium plus on it. That is abbreviated lithium diisopropyl amide, or LDA. It's not bad, it's probably beyond the scope of this class, but it's another one that people use to do this. That's not my favorite lithium base. My favorite lithium base is to take the nitrogen minus with the lithium plus, and then take and add a silicon to that, and then place off the silicon 3 methyls each, which makes it super sterically hindered, but it has the same characteristics. It's a sterically hindered strong base, but it's a little bit easier to work with. It doesn't decompose as easily. So I've used that various places since I was in graduate school. So you'll see those in the book as well. The purpose is strong base that's sterically hindered. So what I'm doing right now is I'm setting up that if I want to do this E2 reaction, I'm either going to use a small base that doesn't act as a nucleophile, or I'm going to use a sterically hindered base that can't act as a nucleophile because it's sterically hindered. And then the question becomes, how do they react differently in these E2 reactions? So let's take our 5-minute break or so, and then we'll talk about the intricacies of these reactions. It's first semester lab's a little rougher than second semester.
So it gets better.
No, next semester we're going to spend the first 4 or 5 days doing spectroscopy. So it may or may not get better. You'll have to see. Okay, back to E2. So E2, I'm going to use my strong base, small or big, to do the reaction. Now, a couple of important details about E2. There is a stereochemistry requirement for E2. And what do I mean by that? Well, in order for me to explain this stereochemistry requirement for E2, let me explain why there was no stereochemistry requirement on E1. So when you took your leaving group and you lost your leaving group to form the carbocation, to form your carbocation intermediate in E1, remember the carbocation intermediate has those two lobes of electron density, and the carbon has a positive 1 charge. And I need to go back actually to I need to go back to SN1 here for a moment as well. But let's start with this. So when you have a carbocation, you have these two lobes of electron density. To lose the beta hydrogen, what you have to do is you've got to line up its bond parallel to one of those two lobes. So this lobe has to be parallel. It has to be parallel to the empty p orbital. And if I write that sort of if I write that horizontally, that means that it would look like this for that carbocation. So this is my alpha carbon that still has a positive charge. This is my beta carbon. That's my beta hydrogen that I'm going to lose. In order for me to lose that beta hydrogen that's in the square, that beta hydrogen carbon bond has to line up perfectly parallel with one of these two empty lobes. So that as the hydrogen gets pulled away, and this is E1, so it's not really pulled away, it's falling away. As it falls away, this lobe then, that sp3 hybrid orbital, will then become, as you lose the hydrogen, it'll become a p orbital, because now I'm going to form my double bond. And now that p orbital with a pair of electrons in it, because I lost my H plus, is now going to be parallel to the empty p orbital, so that then now they can overlap to form the pi bond. So when you're doing E1, you always lose the hydrogen that is parallel. The bond is parallel to an empty p orbital, and you have a top and a bottom here. So that hydrogen could be parallel to the top empty orbital, or it could be parallel to the bottom empty p orbital, but it's got to be parallel to an empty p orbital. So for E1 to lose that H plus, it's got to be parallel to an empty p orbital. But it has two choices. It can either be parallel to the top or the bottom. Now, that's different than E2. So this is E1, so that means the hydrogen could be parallel to the top orbital, or it could be down here parallel to the empty orbital. That's going to have a huge implication when it comes to rings. Because if I'm going to do an E2 reaction or an E1 reaction on a ring, then I need to know, am I going to lose the beta hydrogen that's cis or trans to the leaving group? But let's do E2. So in E2, it's a different mechanism. And in this case, what has to happen is that the beta hydrogen that's going to be removed, by the base, when the base comes in and grabs that beta hydrogen has to be what's called anti-periplanar. It has to be anti-periplanar to the leaving group. What does that mean? It means exactly what it says. This hydrogen bond has to be planar to that leaving group, and the hydrogen has to be anti to the leaving group. So the only way that that hydrogen, that beta hydrogen, is going to be removed is if it's anti-periplanar to the leaving group. If I was over here looking down that carbon-carbon bond, that means if I write my Newman projection, that means the beta hydrogen and the leaving group have to be anti to each other. The periplanar just means in the same plane. And I actually think that's out of vogue now. Anti-periplanar, I think it's, I don't know what the term is because it didn't make any sense to me, so I just keep using anti-periplanar. So that's what's required of the stereochemistry. So we'll come back to that. But that's what's the stereochemical requirement for an E2. So for an E1, the hydrogen can be on either side. The hydrogen could be coplanar to the leaving group. Well, actually, there is no leaving group. So the hydrogen can either be planar to the top lobe or the bottom lobe. Once the leaving group leaves, then we form the carbocation. So the reason for this is simply because we want the transition state and the reaction to be efficient. So the way this works is, again, remember our sp3 hybrid orbitals, they got a big lobe and a little lobe. So they look like that I just colored in. So what's going to happen is as you lose the H plus in the leaving group, those orbitals are going to move to become p orbitals. So they're going to slide up. And not only do they slide up to become parallel to each other, but this lobe and the tiny lobe here begin to even out. So as it's moving, this one's becoming smaller and the tiny lobe's becoming bigger. So then when they get to the transition state, it's two p orbitals, so that when the H plus leaves and the leaving group leaves, those two can now overlap to form then the final pi bond. So the orbital picture is that's just the easiest movement of those orbitals in order to get the pi bond. And remember, the transition state's all about less movement, less energy gives you the lowest activation energy. So this reaction is going to move to give you the lowest activation energy. It's not going to want an abnormally high one. So if those p orbital, or if those two, the hydrogen and the leaving group, are not periplanar, if they're not anti, they got to become anti to react. Okay. Everybody kind of with me there?
So if the initial molecule is not anti-periplanar, and you add the reaction can still go, but it'll just rearrange itself.
Exactly. So, your book has lots of these problems in it. The top hat has a lot of these kinds of problems. Look what we're back to. Our friend the sawhorse projection. So let's say we take this molecule and react it with a strong base in an E2 mechanism. Which carbon's my alpha carbon? The right carbon is the alpha carbon, the left carbon is the beta carbon, and there's a beta carbon up here. Okay? Now, that means I could get two products from this reaction. In other words, if this is beta carbon 1 and this is beta carbon 2, I could have this B minus come in and attack beta carbon 1 or remove beta hydrogen 1 and form the double bond up there. So in other words, what could happen is the strong base could come in, grab this hydrogen, have this pair of electrons move down here, and kick the bromine off. And if it did that, what would the product look like? Well, the left-handed chirality would not change. And all it would end up with the CH2 there, and then the hydrogen there. So that would be my product. Where we agreed that double bond could form there. So a double bond could be formed between the alpha carbon and the beta carbon 1, and so that's what the product would look like. We haven't done anything like this, right? My strong sense of deja vu here is not for this class, but the fact that let's see, this is July, that I just went back through that I just did this in May. No, April, late April. With the organic 2 class. And we'll do it again in another month anyway, for another reaction. So that's one product, but that's not the most interesting product. The most interesting product is when my base comes in and removes this beta hydrogen, and I do my E2 reaction, I'm going to get two possible products. Because now I'm going to form the double bond between that beta carbon and that beta hydrogen, or that alpha carbon. So there are two possible products. So the question is ultimately here, which of those two alkenes do I get? Do I get the product with the two methyl groups cis, or do I get the product with the two methyl groups trans? And what did you have to do to get that answer? So, when the base removes this beta hydrogen in the square on beta carbon 2, which of those two products am I going to get? And I'm only going to get one of those two. So since the base is doing an E2, that means this reaction is E2, and it has to be anti-periplanar. The product has to be anti-periplanar. Or sorry, not the product. The transition state has to be anti-periplanar. Which means the hydrogen in the box has to be anti-periplanar to the bromine. So you must put the molecule in that conformation before you can do the elimination reaction. Is it in that conformation? Is it in the correct conformation now? Is this hydrogen in the box anti to the bromine? Yes or no? No? Where does it have to be anti to the bromine? Where the methyl group is. So I need to take this molecule and I need to, do I have to do anything to the right, to the carbon on the right? No. But I'm going to have to do what to this carbon on the left? I'm going to have to rotate the hydrogen up here, the methyl group down here, and the ethyl group into the back. In order to put the hydrogen there, then bring the methyl group here, and then move the ethyl group to the back. So I've got to rotate that group in order to put the hydrogen anti-periplanar to the bromine. Now is it in the right position? So so E2 must go through an anti-periplanar transition state. So if the hydrogen is not anti-periplanar to the bromine, if that beta hydrogen is not anti-periplanar to the leaving group, you've got to make it anti-periplanar first, and then do the reaction. If you can't put that hydrogen anti-periplanar to the leaving group, then it can't be removed by the base. So is rearranging it the first step? Yes. To form the second product. See, this was product number 1. Now I'm looking at product number 2. And so what's product number 2? It's either A or B. And so in order to figure out whether it's A or B, I've got to put the hydrogen now anti-periplanar to the bromine. So have I done that? Yes. So now the base will come in, the base will grab that hydrogen, pair of electrons moves here, pair of electrons, the bromine gets kicked out. I'm now going to form my double bond. Which two groups are going to be cis? The groups that have the same arrows or the same bonds are going to be cis. So the two bolds are going to be cis and the two dashed are going to be cis. So in this case, the methyl groups are going to be cis, and the two dashed groups are going to be cis. So this is the only product of that that's the only product of losing that beta hydrogen. Losing beta hydrogen 2 over here is only going to give me that product with the methyl group cis. Where the methyl groups are trans is not possible to be formed.
So whenever you bond form, the hydrogen leaves
Let's look at this down the. Let's look at the transitions, or let's look at a Newman projection here. So when you look at this as a Newman projection, the hydrogen on the left, the ethyl group's going to be away, and the methyl group is going to be in front. On the right-hand carbon, the methyl group's going to be on the front, the hydrogen's going to be in the back, and the bromine's going to be down. So when the base comes in and grabs this hydrogen and this bromine leaves, the other two groups come together. The groups on this side are going to now become parallel to each other, and the two methyl groups are going to become parallel. So the final product in a Newman projection would look like this. You're going to have the double bond look like that. It's going to look like that with the groups planar. So this is looking, so that's like over here looking down that carbon-carbon bond. So the groups that are on the same side there are going to squish together to become cis, and the other two groups are going to come together to become cis. Over here, that means the two bolds are going to become cis, and the two dashed are going to become cis. So to do E2, if you have a molecule like this where I've shown stereochemistry, or if they show you stereochemistry like this in the book, you've got to put the hydrogen to be anti-periplanar to the bromine. B isn't an option because this is the only conformation where this hydrogen is anti-periplanar to that bromine. And so when the base comes in and grabs that hydrogen, the bromine leaves, the groups that are bold are going to become cis, and the groups that are trans are going to become cis. And so that's how the geometry gets set up. If the geometry was such that the methyl groups were one bold, one dashed, then they would end up trans, but in this case, they're cis. So this geometry then sets up the transition state to this geometry gives that product. They're both the products of this reaction. So product number 1 is this one. And product number so this is product number 1, this is product number 2. So those are the two possible products of this reaction. Now, can I choose one over the other? Yes. We're just about to get to that point. So this is one of the nuances of E2. It's got to go through an anti-periplanar geometry. So in chapter 9, there's a bunch of these problems where they give you two stereochemistries and they say, what's the final alkene? And so you've got to put it so that that beta hydrogen and that leaving group are anti to each other before you lose the H in the leaving group, and then they come together to form then they come together to form the alkene. Now, can I choose one over the other? Yes. I could choose one, or I could choose two. Do I want to do that with this molecule? No. Personally, I like this one. This is the molecule I like. Alpha carbon, beta carbon 1, beta carbon 2. Each of the beta carbons has hydrogen, so I'm good. This is beta hydrogen 1. This is beta hydrogen 2. If I lose beta hydrogen 1 from the base coming in and ripping it off, I'm going to form 2-butene. If the base comes in and grabs hydrogen 2, I'm going to form 1-butene. So I'm going to get product 1 or product 2. If I did this reaction using E1, what would be my major product? If I do this by E1, what's the major product? Number 1? Do we all agree on that? Okay. So how am I going to choose? I got two bases here. There's my two bases, NH2- and tert-butoxide. What's their difference? So I've got a big sterically hindered base and so I've got a sterically hindered base and I've got a small base. So what? Well, in order to do E2, you've got to be able to form the transition state, which means that the base has to get close enough to rip off beta H1 or beta H2, right? Do we agree with that? If you can't form the transition state, can't do E2. Now in this case, there's free rotation. and there's actually 3 hydrogens over here on beta H2. So there's going to be no problems in either of these cases with forming an anti-periplanar geometry. So how easy is it for NH2 minus to get to H1 or H2? Sterically. Can it get to H1? Be easier getting to H2, but can it get to both? Yes. It can get to both. How about the sterically hindered tert-butoxide? Which one is it going to be easier for it to get to? 1 or 2? 2. What kind of carbon is beta carbon 2? Primary, secondary, tertiary? Primary. Beta carbon 2, or beta carbon 1, sorry. What kind of carbon is that? Primary, secondary, tertiary? Secondary. So, I can select which beta hydrogen I'm going to remove by using the base, the appropriate base. So the sterically hindered base is going to have a much more difficult time getting to beta hydrogen 1. Do we agree on that statement? The sterically hindered base is going to have a much more difficult time getting to beta hydrogen 1. So which base is it preferentially going, or which hydrogen is it preferentially going to remove? Number 2. Okay. And so the tert-butoxide, the major product the tert-butoxide is going to give is number 2, 1-butene. Now, what's the technical reason for that? The technical reason is that the more sterically hindered the hydrogen is from the tert-butoxide, the more energy it's going to take to get that tert-butoxide close enough to grab the hydrogen. So what happens to the transition state energy? It goes up. So the less sterically hindered the hydrogen, the lower the transition state energy. Well, the lower this transition state energy, the lower the activation energy. And so the faster the tert-butoxide will be able to get to beta H2 than beta H1. But wait, product 2 is less stable than product 1. Who cares? My tert-butoxide has to be able to get to the hydrogen in order to start the reaction. So the product energy, the final product energy, is irrelevant. For the tert-butoxide, it's the activation energy that's important, and the activation energy is lowest when the hydrogen is less sterically hindered. So for tert-butoxide, it's going to go to H2. And that's going to be the major product. And that's in the book called the Hoffman product. Although the Hoffman reaction is in the organic 2, and that's what's screwing me up right now, because I could have sworn I did this stuff with you guys, but it's not with you guys, it's with 2 other classes 2 months ago. It's a good thing don't have multiple organic classes in different places at the same time, or I'd go insane. Does that make sense? So tert-butoxide is limited to sterics. It's going to pull off the least sterically hindered hydrogen. Now, how about the NH2? Same thing's true for the NH2, right? It's less sterically hindered to get to 2 than it is to get to 1. But can it get to both relatively easily? Yes. It could get to either one of those pretty equally. So now we have to ask the question, well, it can get to either one. What's the major product going to be? Now, what comes into play? Well, if it can get to either one, it's going to form the more stable product preferentially. And if you don't like that, the tert-butoxide, the transition state energy, is totally based on how difficult it is to get that hydrogen. But with the NH2, those transition state energies, pretty similar. This is a small base. It can fit into either space. But what's driving the transition state energy now is our friend, the Hammond's postulate, which says that the more stable product is going to have the lower transition state energy. So this is the transition state energy is a combination of those two, and in this case, what's going to dominate? With a small base that can get to either hydrogens relatively easily or relatively the same, the final product energy is going to drive by Hammond's postulate. And so in this case, if the NH2 minus can get to both, it's going to form the more stable product. The problem with the tert-butoxide is it can't get to both. It can only get to the one that's least sterically hindered. And so now I have a choice. If you want to remove the hydrogen that's least sterically hindered, use the sterically hindered base. If you want to form the product that's most stable and most substituted, that's going to come from the hydrogen that is the one that's more sterically hindered. Then you use the small base and let the product stability drive the reaction. So I can choose the product I want. You want tert-butoxide? You want product 2 here? Use tert-butoxide. You want product 1? NH2 minus. Now NH2 minus will give you the product that you would get from E1, but the NH2 minus still has to get to that hydrogen, which means that hydrogen still has to be antiperiplanar. So it's always remove the hydrogen that's antiperiplanar first, and then if you can do that, then it's a question of are you going to remove to form the more stable product, or are you going to remove the least sterically hindered hydrogen? And notice I'm saying that way, and I'm not saying it to form the less substituted product, because I can break that rule very easily, and I probably will next Monday after the exam. I've probably just done 3 exams. And Independence Day is screwing up the schedule. Yes. So, okay. So again, I'll send out, topics for the exam on Monday, but it's definitely going to be SN1 now. Well, SN1 and E1, right? Because we've got those two. And then for E2, it's going to be identifying the beta hydrogens that could be lost and writing the products. It could ask you to do a mechanism of an E2, and so the mechanism of the E2 would be what we did here. No, what we did with the base coming in, reacting with the hydrogen to form the transition state, to form this transition state, and then the final product. So I'll give you the list. And then identifying, if I gave you tert-butoxide plus a molecule, the major product's going to be the hydrogen that's going to be lost that's least sterically hindered. If I give you an NH2 minus, it's going to be the hydrogen that will give you the most stable product. And now we're going to have rearrangements. So I'm going to ask you mechanisms, and then I'm going to say write the products of the reactions with or without rearrangement. So those will be SN1, E1, and then I could ask you to write the products of E2. So mechanisms similar to what are on the take-home quiz. So for the take-home quiz, if you just take a picture of it or scan it and send it to me by the end of the day on Friday, I will grade it and send it back to you on Saturday. And then if you have any questions about any of these, feel free to ask. But I'll send out an email later, and that will be what it is. I have 2 extra hard copies of the quiz right here.
I just wanted to double check and make sure that I sent you the question too. Before I click on